distances, and no RF amplifiers were required. It wouldn't light up a light bulb at the other end. As wireless progressed, Tesla established the system where he could transmit longitudinally through the Earth electrical power at a velocity of 291,000 miles per second. Also, he developed a beam tube.
What was that speed?
291,000 miles per second, pi over 2 times the velocity of light.
186,000 miles per second is C. I think you're exceeding C. Maybe kilometers?
No, it's pi over 2 times the velocity of light.
He is exceeding C. He'll go on and explain.
Okay.
There's a different set of dimensions.
All right.
Velocity of light simply is an expression of the ratio of energy to mass.
All right, which is a limit.
A limit to what?
As a constant.
It's a constant,
Yeah.
not a limit. In the beam, Tesla found that he could transmit direct current energy over incredible distances. And this energy not diverging out of the beam, much tighter and more compact than any laser ever built. In the longitudinal mode through the ground, there is really no losses, and the light bulb would light up at the other end. Marconi, in an attempt to circumvent the Tesla patents, changed the impedance of the system and used the flat top antenna, where you would get transverse electromagnetic propagations at 186,000 miles per second and longitudinal magnetic dielectric transmissions at 291,000 miles per second. For those that want to go back through history, Professor Wheatstone proclaimed that the velocity of electrostatic induction was pi over 2 times the velocity of light. As those of you that know about electronics and electricity, I'm sure you've all heard of the Wheatstone bridge. Wheatstone was a very important researcher. As things progressed, we ended up with this. Thanks to Mr. Sarnoff and RCA, all of these things were eliminated, and we ended up with a system where transmission only propagated at 186,282 miles per second. And the losses in the system were total. This occurred in 1919, and by then Tesla vanished from the scene. Now, if we analyze these systems, we find that the longitudinal magnetodielectric system, that the electrostatic lines of force and the magnetic lines of force are directed in the same axis as the propagation of the electrical energy. In the Hertzian system, the magnetic lines of force and the electrostatic lines of force exist at right angles to the direction of electrical energy propagation, and this is what accounts for its incredible losses. In this system, we have little or no losses. In this system, we have an extremely high level of losses. In fact, by its very definition, it's resistance. It's called radiation resistance, a term familiar to many. Now, also, we have the waveforms that these devices produced. Now, we're familiar with the conventional alternating current. Okay, the alternating current has a real frequency in cycles per second. And it constantly cycles in a circular fashion back and forth. And then, of course, we know about the continuous current, or the direct current, which has no cycles per second. This would be called a scalar frequency. Scalar, by definition, is a quantity that does not vary in your system of variation, of either time or space or whatever variation you're talking about. Example would be like atmospheric pressure. Atmospheric pressure is the same everywhere in this room. And that's a scalar function. But if we take the function of the height of people in the room, obviously that's a spatial function. I can see all these waves moving around. So we have a scalar function, and then we have a regular function of variation in this dimension of space within this room. Now we have the waveforms that have become forgotten since the days of spark gap and wireless. One is the impulse wave, which is measured in decibels per second and has an exponential waveform. Where this waveform is expressed in sines and cosines, this waveform is expressed in hyperbolic sines and hyperbolic cosines, and never truly dampens out, but always approaches zero asymptotically. And then we have the oscillating current waveform, and this was the one utilized by Tesla. This waveform is expressed in cycle decibels per second. Now, in Tesla's time, he had a concept which he called individualization, where he would attune his resonant devices to respond not only to the cycles per second, but to the decibels per second, and produce a second order of tuning, more individualized. Carrying this concept on further, if we take the resonant action of a simple LC circuit, it produces a sinusoidal function. But if we take the resonant action of a quarter wave transmission line, shorted at one end and open at the other, not only will it resonate at the fundamental frequency, but it will resonate at the third harmonic, fifth, and ninth, and ad infinitum all the way out. And it will produce this waveform. So we can see where we're in conventional tuning, we're using the sine wave. In the transmission line tuning, we end up with rectangular waves. Now, if we take the resonance of a coil instead of a linear transmission line, which is shorted at one end to ground and open at the other end, the harmonics are in phase, and we end up with impulses. Now, we find with the sine wave, the amplitude is the square root of 2 higher than what we would, rather than 1, it would be square root of 2 higher because of the peak to average ratio. With the rectangular wave, it would be 1. With the impulses, it's infinity. Now, what I attempted to show here is that in a measurable quantity of time, like on an oscilloscope, I used the black to show what we would see on the screen. Now, if we look at a square wave on the oscilloscope, we know that this transition is not visible because the amount of time occupied is infinitesimal. Now, with the impulse waveform, the pulses are of infinitesimal width. What I'm trying to show with the shading here is the integration that shows that the energy contained in the wave is the area underneath it. There is no area on this. The amplitudes are infinite. And these are the waveforms that Tesla were working with. And these waveforms would tend to punch through where the continuous waveforms wouldn't make it. Now, I have a working model here. If I can carry all this over and not get electrocuted. I don't think it's going to work, so I'm going to speak louder. I'm going to have to circumvent.
Take that mic. This is working real well. Not that one, the other one.
Yeah, I don't like being grounded by playing with 600
Yeah,
volts.
good idea.
Okay, I have a model of the Tesla transmission system. I'm going to go over this.
Take the big mic. That's what